All right, so today I wanted to do something a bit different. So I'll be introducing a way that you can use to derive series expansion for different functions, mathematical functions. So some prerequisites that you need to know is you need to know derivatives of these functions, and also you need to know the binomial theorem in general. You know how we write 1 plus x the whole raised to n as nc0 x raised to 0 plus nc1 x raised to 1 nc2 x squared and so on and so forth up to ncn x raised to n. That's how you write it, right? Now this c being here is a notation for like a combination, right? So you can't use anything other than positive integers here, and 0, of course. So the general expression for binomial theorem is going to be just something that is a bit similar, but at the same time, you don't just write it as c. That's the only difference you have. This term is just going to be 1. So the first term is going to be 1, then n into x divided by 1 factorial plus n into n minus 1 divided by 2 factorial into x squared, and then so on and so forth, right? So if you actually nc1, if you expand that, you'll get n divided by 1 factorial, and c2 is n into n minus 1 divided by 2 factorial, and yeah, so on and so forth. So this is what we need here. Okay, so suppose we have a function, say f of x is equal to sine inverse of x. Okay, and you need its series expansion. What you're going to do is you're going to take its derivative, and it's going to be 1 by root of 1 minus x squared, which you can write as 1 minus x squared the whole raised to minus half. Now what I'm going to do is use binomial theorem to expand this. So I can write this as 1 plus minus x squared, right? That'll avoid a lot of confusion while writing this. So you can expand this like this: 1 plus, instead of x, it's going to be minus x squared, and instead of n, it will be minus half here. Now, the beauty about writing it like this is because there's no c notation here. This is still valid. I'm not going to the proof and stuff about how it's valid for fractions and negative integers or whatever. You just got to take my word for it now that it is going to be valid for fractions as well. So we have minus half here, minus x squared. This n is going to be minus half, minus x squared is going to be there in place of x, divided by 1 factorial, plus minus half minus 1 is minus 3 by 2 into, we have minus x squared here, divided by 2 factorial, and so on and so forth. So the first term, if you simplify this, negative becomes positive. X squared divided by 2, 2 factorial is 2 itself. 2 into 2 is 4, 4 into 2 is 8. So 8. This, there will be minus into minus is plus, plus into minus is minus. So this becomes a minus 3x squared plus so on and so forth, right? 3x squared by 8. So this is going to be our f dash of x. So what you need to yield the function sine inverse x, you just need to integrate it. So if you integrate this with respect to dx, then, sorry, with respect to x, this will be just x. This will be x cubed divided by 2 into 3. This will be 6, right? Minus 3 by 8 into x raised to, oh, sorry, this is, I actually forgot something here. There's a square here, right? Because it's x squared. This is minus x squared, the whole squared. So this will be actually positive, my bad. This is a whole squared. So this term will be positive, and these two negatives will cancel out to be positive. So this will be 4 raised to 4. Okay, so this will be x raised to 5 by 5. and so on and so forth. So we get sine inverse x, and plus c will be there as well because we are doing an indefinite integration here. Sine inverse x is equal to x plus x cubed by 6 minus 3x raised to 5 by 40 plus so on and so forth plus c. Okay, now to figure out what this plus c is, you can just put the values into the function. You know that sine inverse of x, this is the function, right? Sine inverse of x, we got that as x plus x cubed by 6 minus 3 by 40 x raised to 5. So it's not minus, this is plus. my bad. Plus this all the way up to plus c. These are all terms of x. If you put x equal to 0, this implies this whole thing, it becomes 0. And then you have plus c. Now we know sine inverse of 0 is 0. So that means this constant of integration is also 0. Okay? So from that, you'll get the series expansion of sine inverse x is this. You can do the same thing for cos inverse x as well. Now, let me write this as g of x is equal to cos inverse of x. The only difference here is that if you take this derivative, g dash of x is going to be minus 1 by root of 1 minus x squared. So what you'll get is around the same thing, but just with a negative sign. So that will be, now we'll pose a little bit of a problem. That's why this plus c becomes a little bit important here. So I'm just going to directly skip to this step, and I'm going to write g of x as minus of x plus x cubed by 6 plus 3 by 40 x raised to 5 plus so on and so forth. If I did not have this plus c here, then that means sine inverse x plus, this is cos inverse x, right? Sine inverse x is equal to minus cos inverse x. Or that would imply that sine inverse x plus cos inverse x is equal to 0, which we know is not true. But that's where this plus c is very important. Let me name it as c dash. If I put it as cos inverse of 0, you know the value of cos inverse of 0 is pi by 2, and this whole term becomes 0. So c dash is equal to pi by 2. So this constant becomes important here, because, and now it makes more sense because we know sine inverse x plus cos inverse x is equal to pi by 2, right? So yeah, that's what we get here. These two, this term, this whole thing with the x, the expression with x, that gets cancelled with that of sine inverse x here, and the only term remaining will be the constant, which is pi by 2. So this is all cool and all, but I've only covered inverse trigonometric functions right now. You can also do it for tan inverse x as well, and obtain its series. I will be not doing that here. I'll leave that up to you as an exercise. It's the same process really, but as I've said, I've only covered inverse trigonometric functions here. So what about normal trigonometric functions? Now, the thing about the normal trigonometric functions is that we cannot directly derive them from derivatives, because if you take, say, if you take sine x, its derivative is going to be if you take its derivative, is going to be equal to cos x. Cos x derivatives is going to be equal to minus sine x. So it will just go on in like a back and forth loop, and we won't really be able to derive a series for that. So to derive the series for trigonometric functions, we would have to take the help of, this thing, the expansion of e raised to x. So let me show you how we can derive the expression for e raised to x. Now, this is a bit logic. It's not directly dealing with derivative. It does deal with derivatives, but it's a bit more. It's not as straightforward as this, I'd say. So again, let me take this function. This is e raised to x, right? This is the function that we need. We know that this is an exponential function, right? So I'm going to express this in terms of exponents and different degrees. So I'm going to write this as a0 plus a1x plus a2x squared plus a3x cubed plus so on and so forth, extending up to whatever. Okay, it's an infinite series, right? So the reason why I'm able to do this, like I said, is because I know this is an exponential, it's a polynomial function. That's why I'm doing this. So what I'll do is I'm going to take its derivative again, which I know is again the derivative of e raised to x is e raised to x. So this is going to be equal to, this is a constant, so this becomes 0. This becomes a1 plus 2a2x, a2x plus 3a3x squared, and so on and so forth. Now what I'm going to do is that I'm going to compare the terms here, okay? So if you look at what happened here, these terms are essentially same, right? That is, we get a0 should be equal to a1, and we also get that a1 should be equivalent to 2a2. And similarly, we get the coefficient of x squared is a2 here. That's equal to 3a3. So from this, in extension, we can say that an minus 1, an minus 1 is equal to n times an from this, from following this logic. So what I'm going to do is that I'm going to multiply all of these equations. And what happens is that when I multiply all of those equations, this side and this side get cancelled, this side get cancelled, and only the constants get multiplied up to n. So here, up to the previous stage, these and these get cancelled, these and these get cancelled, these and these get cancelled, these and these get cancelled. So what you'll get essentially is this a0 is equivalent to 1 into 2 into 3 up to n times an. Or this can be written as n factorial. Or in other words, an is equal to a0 divided by n factorial. So that's kind of great. If we can figure out what's a0, we can figure out what a1 is, a2 is, and so on and so forth. Any term, any nth term, we can write it down. So what I'll do for that is, again, I can just put the value of the function. That is, if I put x equal to 0, e raised to 0, we know that e raised to 0 is 1. And if we put x equals 0 here, all of these terms become 0. So that means a0 should be equivalent to 1. So that means I'm plugging that in here. So you get an is equal to 1 by n factorial. Okay? So from this, we can technically conclude that the series for e raised to x is a0, which this a0, we got it as 1. a1 is, according to this, 1 divided by n is 1, so 1 factorial into x, plus a2 here, according to this, is 1 by 2 factorial into x squared, and so on and so forth. So this is going to be a series of e raised to x. Okay? Now, here we need another prerequisite actually for trigonometry that I forgot to mention. That is, I don't know what this is exactly called. I think it's the Euler's representation of imaginary numbers. And that is, you can write e raised to ix. If instead of x, if you put ix, I is the imaginary number, you can write this as cos x plus I sin x, where this is the real part and this is the imaginary part. So to get the series expansion of cos x and sin x, all you need to do is just put ix in here and separate the real part and the imaginary part, and you'll get the series for cos x and sin x. So if we put that here, this will be 1 plus, instead of x, it'll be ix divided by 1 factorial, plus, instead of this, it'll be I squared, which is going to be minus 1, times x squared divided by 2 factorial. Then again, it's going to be ix the whole cube, which is going to be minus I into x cubed divided by 3 factorial. Then the next term is going to be ix the whole raised to 4, which is x raised to 4 divided by 4 factorial, and so on and so forth, is equal to cos x plus I sin x. Now, if you separate the real parts, this is the real part, this is the real part, this is the real part, you'll get the series for cos x, and if you separate the imaginary part, you'll get the series for sin x. So cos x, we will get it to be, cos x will get it to be